So we're talking about models of the atom and the discoveries and scientists that brought us to our current understanding of the atom and the smaller and smallest particles of matter, such as electrons, protons, neutrons, and other. So in 1911, or 1910-11, Rutherford discovered the nucleus, and soon after discovered the proton, and theorized the neutron, and that was soon discovered as well. And a result of Rutherford's nucleus is that nuclear theory, the orbital model of the electrons orbiting the nucleus. But that didn't work very well, as you know. So it was very soon after that Niels Bohr proposed a quantum mechanical model of the atom, but it wasn't. It was more about he was not able to give the reasons for why it was a quantum atom or why it acted the way it did, but all that Bohr was able to fix the problems with Rutherford's classical planetary orbit model, 1913, with quantized orbits. Bohr simply said that the orbits are quantized, that the electron will stay there and it will not emit energy in these fixed orbits. It will only emit energy when it changes an orbit, but it does not emit energy while it's in a fixed orbit, so it's not forced to change orbits just because of the fact that it's orbiting. That was the biggest problem, of course, with the planetary orbit model, the classical planetary orbit model, because it radiated energy at all times and therefore wouldn't stay in orbit. Bohr starts by saying that the orbits still occur because of the Coulomb force. That's why the electron is trapped in the atom. That each of these quantized orbits that the electron can be in, it can be in orbits of different radius, that each of those quantized orbits have a unique energy, which makes sense, that even in the classical atom, if it's at a different radius, it's at a different energy. But here's where we have to differ, particularly from the classical orbits, is that each orbit that the electron might be in is a stationary state that does not radiate energy. So that's something new. It's a stationary state that doesn't radiate energy. And that the only time that a atom or an electron will radiate energy is if the electron changes its orbit. So one of the things that I think maybe I wasn't as clear about is these quantized orbits they're not just any orbit. You can't just be at any radius that's fixed. That there are only certain allowed quantized orbits. And that point, along with the last point, the second point along with the fourth point in particular, are what predict the atomic spectra that we see, because there are only certain allowed orbits of particular energy, and if an electron jumps from one higher energy, let's put an electron here, jumps from one higher energy down to a lower energy orbit, it will then emit, let's do a different color, it will then emit electromagnetic energy in the form of a photon of a certain color, which is equal to the change in energy of that orbit, delta E, right? So if this orbit has energy E2 and this orbit has energy E1, then delta E is E2 minus E1, and that is going to be the energy of the electron, right? So delta E, not electron, sorry, of the photon that is emitted when it radiates energy while it changes orbit, delta E equals HF. That's what determines the color of the photon that's emitted, and that's what gives you the atomic spectra, that there are only certain transitions, certain energies, therefore certain transitions that are allowed in a given atom that only allow for a certain color or certain set of colors that you see, hence atomic spectra. And lastly, Bohr predicts that these stationary states, the fixed orbits that the electrons can be in, exist because of the quantization of angular momentum. And it's that fact that he's not able to explain why the angular momentum should be quantized, but he explains that the angular momentum is quantized, and that's what, therefore, allows for these stationary states, and he quantizes angular momentum by this quantity h bar. H bar is actually Planck's constant, but it's Planck's constant. Well, it's Planck's constant over 2 pi. It's h bar. It is a quantity. Either h or h bar are quantities that are used in quantum mechanics all the time to quantize. They're very, very important quantities. And sometimes if there is a 2 pi involved, right, this is something going in a circle, so you might imagine there's 2 pi involved. But anyway, if there's a 2 pi involved, then it's h bar. Well, anyway, that's the definition of h bar. Okay, so quantized angular momentum, n, remember, is an integer. That just says it's quantized. That angular momentum only comes in chunks of h bar, chunks of h over 2 pi. He couldn't explain why, so this is not a complete description of the atom, but this description works now to explain some of the unknown that we have at this point. So let's go ahead and take the postulates of the Bohr atom and put them together in some equations and see what it predicts. So first, the Bohr atom still predicts regular orbits, right? Circular orbits or regular orbits, so that they would have an energy which equals to 1/2 mv squared minus no different than the classical nuclear model, ke squared over r squared. Whoops, is that squared? Tell me, is that squared? I think that can't be because that's energy. This is kinetic energy. This is potential energy. kqq over r minus kqq over r. Right, so k is 1/2 mv squared. U is minus k e over r. Okay, so that's the total energy. Newton's second law tells us that the force, which is ke squared over r squared, is equal to mv squared over r. This is still just like the Bohr atom. That's Newton's second law. This is energy. And then the third new thing that we've got here is that the angular momentum is quantized. So what that means is if we take our nucleus and we take our electron, what color was the electron? I think we had it blue. And that electron goes around. It's got a mass m, or m sub e. It's got a radius r, and it's got a speed v. So it's still sort of classical in that sense. And the angular momentum, so this is what you need to remember from first year physics, is angular momentum is RL is r cross p, which in this case, because the momentum, or r cross mv, they're at right angles to each other, so it's just rmv. And that momentum is quantized, so that equals nh bar. We can then solve for this for v and plug that in there to see what that tells us. Since everything else I think is constant except for r, we can solve that. Yeah, everything else is a known constant except for r. And this tells us about the radius of the orbits. So this is going to show us, let me just go ahead and do it. So v is equal to nh bar over rm, and then we plug that in so that ke squared over r squared equals m nh bar over rm squared over r, and solve for r. So therefore r is equal to m, let me get this right, get the radius of the orbits, and these radii, notice, are going to be dependent on the quantum number n, right? N is the quantum number. N is the quantum number. It is 1, 2, 3, 4. 0 doesn't make sense, right? 0 would be no radius. Quantum number equals 1, 2. It's an integer starting with 1. H bar is a constant. M is the mass of the electron, because we could put an m sub e. K, don't forget, that's the Coulomb constant, 1 over 4 pi epsilon 0. And E is the charge of the electron. So this tells us the radius. So we can say, oh, okay, so the smallest radius, R1, is going to be h bar squared over meke squared. Plug numbers in, and we get 0.529 angstroms. Angstrom is 10 to the minus 10 meters. So that is half of 10 times 10 to the, half of 10 to the minus 10 meters, right? We knew that the atom was around 10 to the minus 10 meters. This predicts, the Bohr atom predicts that the radius of the atom is around that for a single electron atom. That's a single electron atom. And then it's got other allowed radii, but it doesn't, not any radius is allowed. The other allowed radii are allowed by this, right? So the next radius is going to be, so therefore r sub n is equal to n squared times r sub 1. So if we give, I'm not saying if we add an electron, I'm saying if we give that electron some energy, so we add energy. We've been talking about the atoms emitting energy, right? That the electrons emit energy to give you this atomic spectra. But in order to make it emit energy, we got to add energy first, right? So when we actually did the atomic spectra example, we were adding energy by adding electricity to excite the atoms. And then when they fall back down to lower energy states, they emit the photons. So the higher radii, for example, for n equals 1, it's 0.529 angstroms. For n equals 2, it's going to be 4 times that. It's going to be about 2 angstroms. For n equals 3, it's going to be 9 times that, 4.5 angstroms, etc. So the electron will, as we add energy to the atom, if we give the electron energy, it will go up to higher radii, but those radii are fixed by this, right? So this is n equals 2, and there's a third, n equals 3, and the actual radius, that's the energy level. We can call the energy level the n equals 1 energy level, the n equals 2 energy level, the n equals 3 energy level, or the orbit, the n equals 1 orbit, the n equals 2 orbit, the n equals 3 orbit, and the radii are going to be given by this formula, and the energies are going to be given. Let's see what kinds of energies we've got. Let's check that out. What are the energies of each of these orbits? The energies, we're gonna have to go ahead and take r sub n and plug that in there, and v sub n, right? This is v for each quantum number. Plug that in there. You can do that pretty easily on your own. And what we end up getting, right? Again, we are doing this for a single proton, single electron atom. We're doing this for z equals 1 for a single electron atom. And so just to note that we could do this same analysis for an atom with any number of protons, z, and so that would just say that for E sub n is equal to minus z squared, you're going to get, because there was a z for each of the e's, z squared k squared e to the fourth m sub e over 2 h bar squared n squared for any atom. Z equals 1. What atom is that? That's the hydrogen atom. Z for any atom. Okay, so there's nothing different there, but let's look at the hydrogen atom. The value of this is E sub n equals minus 13.6 eV over n squared. Plug in your numbers and you get minus 13.6 eV over n squared. So the lowest energy state, E1, is minus 13.6 eV. So again, drawing full circles because I'm bad at drawing circles, but so we've got these allowed orbits, and they are quantized. And so we can refer to each orbit as the quantum number, n equals 1, n equals 10, n equals 3, n equals 4. But each of those has a radius, r sub 1, r sub 2, r sub 3, r sub 4, etc. And higher, right? There's an infinite number of allowed orbits. They're just defined by these r sub n's. And then each of those orbits has an energy, E1, E2, E3, E4. And then if you move between the orbits, right, don't forget that the change in energy between the orbits is just, between any given orbit is, E, what would we say, ENF minus ENI. Wherever we finish and start, we don't necessarily just go from this orbit to this orbit. We might, what an ugly color. If this is my electron, we might go from this orbit to this orbit. And so then we would emit a photon equal to E4 minus E2. Or if we excite an electron from this orbit to this orbit, then we would have to put in energy. We would have to add energy equal to E4 minus E1. We'd have to add that much energy to the system. Okay. This is, oh, right, sorry, never mind. Let's look at these numbers. So that's minus 13.6 eV for the hydrogen atom. And that would be, if there was a Z in there, it would be E1 is equal to Z squared times minus 13.6 eV. For example, for a helium atom, E1 is equal to, helium is equals 2, so 2 squared times minus 13.6 eV is the is the lowest energy. So that's 4 times 13.6. Lowest energy state of the helium atom. I think I did that right. Just multiplying 4 times 13.6. Okay. And what does the minus sign mean? Remember, what does the minus sign mean? This means it's a bound state, right? That the electrons are bound to the atom. So as I get to a higher radius, they're less bound to the atom, right? Go from n equals 1 to n equals 2 for the hydrogen atom. For n equals 2, E2 for the hydrogen atom is minus 13, so just that, we're doing that, minus 13.6 EV over 4. So that's not for the helium atom, that's for the n equals 2 level of the hydrogen atom. This was just an aside. And that is minus 13.6 divided by 4 is about 3.4, if I have that right, and don't worry about it if I don't, but you get the idea. 3.4 eV, that's the second energy level. Notice that's closer to 0. The first energy level was 13.6, negative 13.6. The second energy level is minus 3.4. The third energy level is 13.6 divided by 9. It's closer to 0. The fourth energy level is 13.6 divided by 16. It's even closer to 0. The fifth energy level is minus 13.6 divided by 25. It's even closer to 0. Notice that what's happening to the energies is that the ground state, the lowest energy, is n equals 1. The next energy, n equals 2. The next energy is closer, n equals 3. The next energy is even closer, n equals 4. It's kind of hard to draw it. And they bunch up, but they never quite reach 0, right? So n equals infinity would be an energy level. E equals minus 13.6. E equals minus 3.4. E equals minus ... right? They get closer and closer to 0, so they bunch up as we get closer to 0, as we get up to higher and higher energies in the atom, until we give the electron enough energy that its energy becomes positive. Then it's no longer in one of these bound stationary states, and it can escape. And that's ionizing the atom, right? So what is the ionization energy for the hydrogen atom? I'm waiting. What's the ionization energy? It's 13.6 EVs. If we add 13.6 EVs, we can knock an electron out of the atom. But anything less will not knock the electron out of the atom. Well, I guess you could theoretically say, well, if the electron's already in a higher energy state, then it would take less energy to knock it out. But hopefully you get the idea. Okay, and then if we talk about a different atom other than hydrogen, we're going to have to just multiply everything by z squared.